Good. So, quick review of what we started yesterday, vector equation of a line. You could write any point on a line by starting with any point and then getting its direction vector b and then going along the line in the right direction a certain distance will get you to another position vector, which will give you another point on the graph. Then we learned if we have some point on the graph x comma y, and we have a starting point which is a and a direction vector which is b, that you can make the parametric form of the line, where you look at the yellow ones, which are the x coordinates, and the y ones, which are the y coordinates. And just as the bell went, we were getting to the Cartesian form. So those previous two equations, you can rearrange them to solve for t. In the one, you would get x minus a1 over b1, and the other one, you'd get y minus a2 over b2. And since t is equal to both of them, t here and t here are the same, you can put them together to say that x minus a1 over b1 is equal to y minus a2 over b2. So these are general things. When we go to the specifics, it'll make a lot of sense. So here we go. Example 1. We want to find the vector equation of a line L passing through the point A, 2 comma 5, and parallel to the vector 3, negative 3i minus 4j. So we're going to write all the forms. First form is our vector equation of a line. Any point on this graph, we have a starting point, so we're going to go 2 comma 5. That's a starting point on our graph. And we know that it's parallel to this other vector. So does it make sense that our vector is going in the same direction? So the direction vector for this one will be 3 and minus 4. The parametric form would just be saying our x coordinates will be 2 plus 3t, and our y coordinate would be 5 minus 4t. That would be your x coordinate. Can you see from here, if you wanted to solve for t, you'd move the 2 over and divide by 3? And can you see from this one, if you wanted to solve for t, you'd move the 5 over and divide by negative 4? So as a result of that, we can write our Cartesian and our Cartesian one would look like this. X minus 2 over 3 equals y minus 5 over negative 4. Perfect timing. Okay, on the side here, we're going to look at what does this look like if we did it old school back when we did our analytic geometry, y equals mx plus b. This is what we know. We know we have a point 2 comma 5. There it is, 2 comma 5. This vector 3i minus 4j looks like that. What we need to do is we need to make an equation of a line parallel to this one that passes through 2, 5. So we want to find that equation of the blue line. Now, y equals mx plus b, what are the things you need? You need a slope. You need a y-intercept. We need to find those things out. We're told that it's parallel to that green line. What is the slope of that green line? Rise over run, -4 over 3. You okay with that? That's our slope. So our blue line is going to look like this because it'll have the same slope plus b. How do you find b? Plug in 2 for x and 5 for y. So then you'd have 5 equals -4 over 3 times 2 plus b. So you'd have 5 equals -8 over 3 plus b. Add the 8 over 3 to the other side. And 5 is 15 over 3. So you'd have 23 over 3 is equal to b. So in the end, you would get y is equal to -4/3 x plus 23 over 3. Using our old way, we have to deal with a lot of fractions. Our answer has a lot of fractions because it has a slope, and our y-intercept has a fraction, but this is the equation of the line. What I want to point out is once you've got your Cartesian form, if you wanted to solve for this, for y, all by itself, can you see here you could, fraction equals a fraction, you could cross multiply to get rid of the fractions temporarily. I would have -4x plus 8 equals 3y minus 15. And if I wanted to get y by itself, add 15 to both sides, -4x plus 23 equals 3y. And if I wanted to get y by itself, divide everything by 3. So I'll get -4 over 3x plus 23 over 3. Whoa. Exactly the same as our old way. However, what's really nice about the vector equation of a line as we go back up, you could choose any point to start with. You didn't need just the y-intercept. And with any point, you could just use the direction. This is kind of like our slope. The direction vector is like our slope. Can you see that it's just flipped, though? Because we have our x on top and y on the bottom, whereas slope was rise over run. And always has the y on top and the x on the bottom. And you get the exact same thing. What's nice about the vector equation of a line is we can also do these same kind of things with three-dimensional objects quite easily. All right, example 1 done.